Hello and welcome back. Let's continue looking at logarithms. And we'll be looking at some basic properties of logarithms in this video along with graphs of logarithms. And so to start with, we want to look at some basic properties. So to begin with, when we're looking at log base b of b, we should remember how this works. So if I solve for this really quickly, if I have some scratch work off to the side, if I go log base b of b, and I don't know what this is, I could say that this is equal to y. I can turn any logarithm equation into an exponential form. So this is log base b of b is equal to y. This means that b raised to the y power is equal to b. And we can see that if b is raised to the first power, b to the first power is just b. So this is quite an easy logarithm. Log base b of b is just 1. b to the first power is 1. Also, if I want log base b is equal to 1, again, I can solve this by turning this into an exponential form. So this is saying that b to the y power is equal to 1. And 1 is a special number with respect to exponents. Anything to the 0 power is 1. So b to the 0 power is equal to 1. This means that log base b of 1 is equal to 0. It doesn't matter what b is in either of these instances. The log of something with itself as the base is always 1. And log base anything of 1 is always 0. Which means that sometimes logarithms are really easy to solve. Log base 9 of 9, that's just 1, since 9 to the first power is 1. Sorry, 9 to the first power is 9. Here, I have log base 8 of 1. Well, this is asking 8 to which power is 1? Well, 8 to the 0th power is 1. Any log base anything of 1 is always 0. This is just a couple handy things to keep in the back of your mind. We also have the inverse property of logarithms as well. For this first one, log base b of b to the x is always going to be equal to x, and b to the log base b of x is also equal to x. And this is because log base b of x and b to the x power are inverses of one another. This is how we defined the logarithm function to begin with. And what happens when you combine inverses? You're going to get x by itself. So for this first one, if we said that this is f of x and this is g of x, then if I write f of g of x, well, this is just f of b to the x, which is just going to be log base b of b to the x. And since these guys are inverses, we just get x. The same way in reverse, g of f of x is going to be g of log base b of x, which is going to be b raised to the log base b of x, which is just x. So again, the fact that these guys are inverses mean they cancel. If you have the same base and you have both a logarithm and an exponent, they're going to cancel and you just get x. So down here, if we have log base 7 of 7 to the 8th power, again, we have the same base, we have a logarithm, we have the exponential function, they cancel out and we get 8. Here I've got 3 to the log base 3 of 17. Again, I have an exponential, I have a logarithm with the same base, they cancel out. So it's quite nice in those situations. So let's look at the graph of f of x is equal to 3 to the x power and use the fact that it's the inverse of this graph to graph the second one. So f of x is equal to 3 to the x power. Let me label we just want 1, 2, 3, -1, -2, -3, and if I start graphing the first function, f, if I plug in, let's say a 0 in here, 3 to the 0 power, anything to the 0 power is 1. 3 to the first power is going to be 3. 3 to the -1 power is going to be 1 over 3, is going to be a third. And we have our exponential function, need steadier hands, is going to look like this. We have this exponential growth because we have base of 3. That means anytime we go over 1, we're going to triple in height. So starting from here, we'll triple in height to there, we'll triple in height to there. But they're both so small, tripling doesn't do much. Here we've started to triple, here we've started to triple, and we're going up a lot faster. The nice thing about inverses is that they have reflectional symmetry. So if we draw the dotted line for the line y is equal to x, we have reflectional symmetry. So here is our f function, which is our exponential. Our log function is going to do the same thing. It's going to be flipped over. So instead of passing through 0, 1, it's going to pass through 1, 0. And instead of getting closer and closer to the x-axis, we're going to get closer and closer to the y-axis. And here we sort of shoot up and away. Here we're going to shoot to the right. And in fact, I can do this a little bit better because we know that the following, g of 3 is going to be log base 3 of 3, and log base b of b, it doesn't matter what that b is, this is always going to be 1. So I know log g of 3 is going to be 1 over here, so I can make this a little bit more accurate. So we see that these graphs are just reflections about this. And there's a couple of things that I talked about in this graph. One is, I knew it passed through this point here, and we can see that it's increasing. So let's write down a couple of the properties of this graph. So characteristics of the graph and of the function itself. So the domain of our logarithm is going to be positive numbers. So coming back up to the picture of the graph, the domain of the function is what numbers we can plug into the function. So if this is our graph here, this only exists for positive values of x. This graph never crosses the y-axis, so we never get to plug in a negative value for x. We never get to plug in a negative value for x, we only get to plug in positive values for x. Whereas the range of the graph, even though it sort of looks like it's leveling off, it never levels off completely. It keeps going up and up and up, and we can actually hit any negative number that we want if we follow the graph down, and we can hit any positive number that we want if we go over far enough. The other way to remember this is the domain and range of an inverse are just the range and domain of the original function. Because we're switching x and y values, the exponential function is just going to have the flip-flopped range and domain of the logarithm function. So because for instance, the exponential can only have positive y values, only positive heights, the range of the exponential is all the positive numbers. And likewise, the domain of an exponential, we can plug any number in to this function that we want. So that means that the range of the logarithm is going to be any number. So there's just a couple of ways to remember that. The graph of f of x always passes through 1, 0, because if I plug a 1 into my logarithm, this is just one of the properties that we talked about, log base b of 1 is always equal to 0, since b to the 0 power is always 1. So we always have exactly one x-intercept, and because we never cross the y-axis, we have no y-intercept. And in fact, this is just going to be a vertical asymptote. When b is greater than 1, like the graph that we just saw, the graph is going to go up and to the right. So it roughly looks like this. If b is less than 1, but we still have to have a positive base, just like with the exponential function, this is going to go down and to the right. And I'll draw a picture of this in a little bit. But essentially it's decreasing if we have a too small a base. And like I mentioned before, the graph approaches but never touches the y-axis. So the y-axis is going to be a vertical asymptote. So let me quickly draw this function here. So again, if we have log base 1/2 of x. So f of 1, so again, log base anything of 1 is always 0. So if I plug in a 1, I get 0. If I plug in 1/2, this is also a special case. This is asking 1/2 to what power is 1/2? Well, anything to the first power is itself. So if I come to 1/2, we have this. And we know the rough shape of the logarithm function, so I'll be able to just draw that in. So it's going to roughly come down and to the right. So this is again decreasing. Our base is smaller than 1, so this will end up being decreasing. The y-axis is a vertical asymptote, and it's going to decrease less and less and less, but it's never going to turn around. It's going to keep going down forever. Now that we know what the logarithm function looks like, we can translate it a little bit and transform it. So here I've graphed the log of x base 4. So what happens if we add 1 to a function? Well, we shift the graph up 1. That's all there is to it. So if this was the original graph, we can shift all of these points up 1, and we can get the following graph. It still approaches the y-axis as we go down. It's just everything has been shifted up by 1. So again, we can have a vertical shift by adding 1 to the function. Here, let's look at what happens if we multiply the function by a negative number. So here I have log base 4 of x again. And if we make all of the heights negative, this is a reflection about the x-axis. We're taking all of the positive values and flipping them over to be negative. So down here, if we're approaching negative infinity by going down, for the other function, we're going to be going to plus infinity. Likewise, up here, we're going to be climbing for a while. With our other function, we're going to be falling. So this is going to be negative log base 4 of x. So again, we're just flipping the graph over the horizontal axis because we're multiplying by a negative 1. Now we have to be careful because here we're multiplying the entire function by the negative sign. Down here we're only multiplying x. So if this was our function log base 4 of x, if we're multiplying the x by a negative number, this means that we're flipping all of the x values from positive to negative. Well, here's where x is positive. Here's where x is negative. So instead of having positive values of x, we have negative values of x. This, when we multiply x by a negative number, we're flipping across the y-axis. So our new function is going to look like this. So this is going to be log base 4 of negative x. And what you'll notice is that I put some parentheses here just to clarify that it's log of negative x, not log base 4 minus x, which doesn't really have a meaning. And I will stop here, but we will continue to look at graphs and logarithms in the next video.